Let me begin today by summarizing what we did in the last lecture. So, as you recall, we have been discussing various properties of material, the electrical properties of a material. So, for instance, one of the things that we did is to discuss what is drift velocity, and we had defined drift velocity and obtained its relationship with the current density, and showed that the current density J is related to the electron drift velocity by minus NE times the drift velocity. Minus sign because we talk about the electrons velocity and not the velocity of the charged carriers, which was taken to be positive while formally defining the direction of current. And we had obtained a relationship between the drift velocity and the applied electric field and the relaxation time by a relationship like this, E tau over m. So last time we also defined a new quantity which is called the mobility, and we said that mobility qualitatively tells us how easy it is for electrons to drift when an electric field is applied, and one defines mobility as a positive quantity, which is the ratio of the magnitude of the drift velocity to the applied electric field. And in connection, in terms of the relaxation time, the drift velocity expression, as you can see it, because Vd is proportional to the electric field strength, so this is nothing but E tau over m, where tau is the relaxation time. The mobility is rather a small quantity in case of metals, because we have seen that the tau is of the order of 10 to the power minus 14 seconds or so, or minus 14 minus 15 seconds. And the electron charge is 1.6 10 to the power minus 19. So in spite of the fact that the mass of electron, which is about 10 to the power minus 30, is in the denominator, we still get a number which is of the order of a few tenths of centimeter square per volt second. We in fact calculated for copper, it was found to be 40 to 45 centimeter square per volt second. We said that this is low compared to the mobility of the charge carriers, for instance in case of semiconductors, and that is primarily because there being too many charge carriers in case of the metals, the frequency of collision is a lot more, and as a result we find that the mobility is affected, the drift velocity is small. And so this quantity in case of semiconductors is somewhat large. In fact, we made a statement that large mobility is required for semiconductor devices to function smoothly. We also obtained a relationship between the conductivity and the mobility from our expression for the conductivity in terms of the relaxation time and density, etc. That was Ne square tau over m, and that gave us that this is nothing but Ne mu. Now in case of semiconductors, about which we will be discussing in detail in later sequence of lectures, we have two types of charge carriers. There are of course these electrons which are which contribute to the current, but in addition there are vacancies of electrons, and these vacancy sites, they also move contributing to current, and these vacancies behave like positive charges and they are called as holes. And for semiconductors, the conductivity expression is given by E times Ne, that is the electron density, number density, times the mobility of the electron plus the hole density, which is usually denoted by P times mu h. And these numbers are substantially larger than the corresponding numbers for the conductors. For instance, for silicon, we had stated that the electron mobility is of the order of 1400 centimeters square per volt second, and for the hole mobility is about 450 centimeters square per volt second. Now, this is obviously much larger compared to what we said in case of the conductors. The next thing that we discussed is about the linear relationship that exists between current and the applied voltage for a wide class of conductors, and these are known as ohmic conductor, and the corresponding law is called Ohm's law. So Ohm's law is stated as the relationship between applied potential difference and the current, which is linear, and this is given by V equal to IR, or stated in terms of the current density, this is J equal to sigma E. This ohmic relationship is going to be quite useful to us in our next few lectures, because we assume that the resistances that are given to us, particularly in labs, etc., are usually ohmic. Though we did discuss the departure from linearity that exists in several conductors. Another thing that we talked about is the fact that the resistance or resistivity of a material, it depends upon the temperature in which the material is kept. And we found that for many conductors, there is a linear region, that is, with increase in temperature, the resistance or resistivity rises. And the primary reason is this, that as temperatures increase, the ions in the solid, they start vibrating and they don't stay put in their mean position. And of course, there is a increase in the thermal velocities also, but more importantly, the ions which are fixed, let's say at absolute zero, they start vibrating. As a result, the frequency of collision increases, and that's the reason why the relaxation time decreases, and the correspondingly the conductivity also decreases and the resistance increases. And the relationship in the region where the resistance increased linearly with temperature is given by rho t equal to rho t0 into 1 plus alpha times t minus t0. Now this is in the linear region. This is what we normally discuss. We made a statement that in case the linearity is not valid, to this term you may have to add the quadratic and the cubic terms as well. So now what is T0 is unimportant, because as long as you are in the linear region, then you can choose any point as your reference point and then calculate the temperature rho t, resistance rho at a temperature T, starting from your reference temperature resistance. The last thing that we also did is to talk about the color coding in carbon resistors. These are standard resistors which are available in the laboratories and sold in the market, and on them they have a color band, usually having 4 bands, out of which the first 3 represent the value of the resistance, and the 4th one represents what is the tolerance, that is the to what extent you can take those values to be correct, the error bars, and that is what you can, from that you can read out the value of the resistance that is available in the laboratory. And I had also talked about some quick mnemonic to remember these color coding. Now, before we proceed, let's talk about a few examples. And for instance, last time, just before we concluded the lecture, we wanted to find out that given alpha, value of alpha, which is about 0.004 for per degree Kelvin or centigrade, doesn't matter, for copper, at what temperature rho will double. It's of course fairly trivial, but so what I want is rho must have twice its zero temperature value, and that is given by rho 0 into 1 plus alpha times delta T. So which tells me immediately that 1 is equal to alpha delta T, or in other words, delta T is equal to 1 over alpha, which is 1 over 0.004, and that is 250 degrees centigrade. Well, assuming my rho 0 is resistance at 0 degree centigrade. The usefulness of this linear relationship, particularly in substances such as platinum or nichrome, which have admirable linear relationship or variation of resistance with temperature, is that you can use this to find out the temperature of an unknown temperature of a heat bath, and that is simply finding out that what is the resistance like at the temperature at which you do not know, and comparing it its resistance with a normal temperature. So these are the things that we talked about last time. Let us look at a slightly different aspect of the temperature coefficient of resistivity. Now, we know that when we apply heat, or that is increase the temperature of, let us say, an wire. Now, we have of course made a statement that its resistance increases, but we also know from our discussion of heat that not only the resistance increases, when you increase the temperature of a substance, the length also increases. So there is a change in the length, there is also a change in the volume, which means there is a change in the cross section. Now that would simply imply that our relationship, where we said that resistance R for a given material is simply given by R0 into 1 plus alpha T. If resistivity follows this formula, resistance for a sample will also follow the same formula. Now, the question then is that why is it that we do not talk about the change in the lengths which are associated with the increase in temperature of a material? Now, before we go to that, try to let us recall our discussion of heat. So we know that since we have used alpha as the temperature coefficient of resistivity, which is also normally used in our heat and thermodynamics course as temperature coefficient of increase in dimensions, but let me say that we will use that as the beta. So beta, let it be the temperature coefficient of linear expansion. That is, L is equal to L0 into 1 plus beta T. I know that the volume also increases, and the corresponding expression for the volume increase is V0 into 1 plus gamma times delta T, where gamma is the temperature coefficient of volume expansion, and if you substitute the relationship between the volume and the length, now this can be written as, supposing I take a rectangular parallel pipe as my material, I can write this as L0 cube into 1 plus, so L0 cube 1 plus gamma times delta T is also this quantity cube. So that gives me that gamma to be equal to 3 beta. This is actually something which you have done in your discussion of heat and thermodynamics. Now that immediately tells me that the area of cross section, which is another quantity which is of importance when we discuss the resistance of material, because we had seen that the resistance is linearly proportional to the length and inversely to the cross sectional area. So by area then becomes this quantity divided by that quantity, which is L0 square into 1 plus 3 beta delta T divided by 1 plus beta delta T, which is approximately, if you expand the denominator in terms of the binomial, and this is approximately equal to A0 into 1 plus 2 beta delta T. So thus, with the increase in temperature, my length increases by this formula, my area increases by that formula. But if you recall, when we wrote down the temperature coefficient and calculated change in the resistance when I increase the temperature, we did not worry about these things. Now, what is the reason for that, and is it always justified? So let's look at that part. So first thing is, let us look at the resistance to be equal to rho L divided by A, this relationship. Now, so therefore, if I consider what is the change in the resistance when I increase the temperature. So let's say that the change in the resistance is delta R. Now, which is delta of this right hand side? Now, this I can write as L by A into delta rho plus rho by A into delta L. This is just a normal chain rule differentiation type. Then rho L delta of 1 over A. So that's equal to minus delta A divided by A square, because A is in the denominator. So that is simply L by A delta rho plus rho by A delta L minus delta A rho L delta A by A square. So let me divide both sides by, let me divide both sides by R, so that I get delta R by R. Now remember, all that I am doing is to divide both sides by rho L by A. So I get 3 terms as from the above. I get delta rho by rho, and this term will give me delta L by L, and this term will give me minus delta A by A square. So if you want to consider all the 3 components together, that is change in the length, change in the area and everything, then this is the expression that you must talk about. But why is it that it is justified in most of our deliberations to neglect these 2 terms? Now that's easily realized by looking at the relative magnitude of these things. So let's look at, for example, for what happens in case of copper. I get delta rho by rho, and that is, supposing my temperature coefficient is alpha, and I am looking at a temperature delta T more than my reference temperature, then I get that this is at rho 0, 1 plus alpha delta T minus rho 0 divided by rho 0, and this is approximately equal to alpha delta. And if you know what is the magnitude of alpha, which you can look up from your standard tables, this is about 4.3 into 10 to the power minus 3. Now, if you look at the corresponding thermal expansion coefficient of length for copper, then you find that this quantity, your beta, it's much smaller. Actually, alpha, as I said, is 4.3 10 to the power minus 3, but beta typically is of the order of 2.5 into 10 to the power minus 5. So that tells me that my delta L by L, is of the order of 2.5 into 10 to the power minus 5. And if you look at delta A by A, that happens to be about 5 into 10 to the power minus 5. And that is the reason why we usually neglect these two contributions. But that doesn't mean there are no situations where these are actually negligible. For instance, if you look at a column of mercury, supposing I have a column of mercury in a glass tube, and let's just for fixing our ideas, let's suppose this is a 10 centimeter height. Now, if you look at the corresponding numbers for alpha and beta for mercury, you find that alpha, that is the temperature coefficient of resistivity, this is for mercury, is about 0.309. And beta is smaller than alpha, but nevertheless, it's still 1.8 into 10 to the power minus 4, which is about 50% of that value. Now, I don't really need to worry about the delta A part, because the base roughly remains constant, because I'm not really considering expansion of the mercury here, but I'm actually going to, because the mercury is contained in a glass tube, so therefore the base being made of glass, the cross section remains the same. So therefore, what I have to do is to only consider the two terms that we talked about, namely delta R by R is delta rho by rho plus delta L by L. So this is the point here. Now I can calculate, given beta, what is the new length, what is this length like. So this is given by your alpha times delta T plus beta times delta T. Now look, in this situation where alpha and beta are comparable quantities, though beta is much smaller than alpha in this case. Now I will still have a contribution from this term, because this is small but not that small. This is just half of that. So therefore, in situations like this, one should also worry about what happens in this particular case to the change in the length. Of course, since this is a very special case of a liquid metal, and its container is glass, which is an insulator, I don't worry about the cross section expansion at all. While discussing the analogy with the water in a tube, we said that it is necessary that I need a mechanism. See, for example, I gave the example of a tube which was closed at one end, and there was water flowing in the pipe. This is what happens in a municipal piping system, that the water is supplied to your home, which is continuously there right at the tip of your water faucet, but no water flows out until you actually open your tap. Now, just like that, you need to provide a mechanism for pushing these electrons, so that when you put your switch on, which is equivalent to opening up a tap, what you find is that the current, or the electrons in this case, will start flowing. Now the question is this, that what was supplied by a water pump there, what is the corresponding quantity? Now, for instance, one of the mechanisms by which this is done is by having a battery in a circuit. So basically what happens is this, that like I have a pump which is pushing the water. Now in order to establish a current, I need something which will actually push it. Now let's see what actually happens. So what I have is a battery which provides this mechanism. We will briefly discuss how this is done, but it is something like an electrolytic cell, usually a dry cell, but where there are two terminals. Now what actually happens, you have seen your standard batteries at home, they are 1.5 volt AA batteries or AAA batteries. Now what you find is that there is an end which is marked with a positive sign. That's a positive terminal and this side is a negative terminal. Now actually inside this there are two electrodes, and one of them, so what is known as cathode is connected to this positive electrode. I must alert you at this stage that in your discussion on electrolysis, you have heard that cathode is the negative electrode. And this causes a lot of confusion, because that is true in case of electrolysis, where we pass the electricity to split the solution into its ions. Now what happens in this case? It is the chemicals which split and approach these things. So because of that, the nomenclature cathode and anode have slightly different context, meaning in both these cases. It's much better because of that to stick to our nomenclature. One is a positive terminal and the other one is a negative terminal. So this is, let's say, is the positive terminal that I have. Now, so the positive terminal is that terminal when you connect it to an outside. And this is passing through some resistances, let's call it load for the moment. And this is your seat of the pumping mechanism, which we have called a battery. Now, the current flows from the positive terminal through the load and comes there. What actually happens is that since I know that the charges which flow are actually electrons, so basically instead of the positive terminal being a point from where the positive charges flow out, actually this is where the electrons actually enter in. Now, so what actually happens is this. So let's still stick to our nomenclature of the positive charges carrying a current. I mean, all that you know is the direction of electrons would be exactly opposite. But supposing we still talk in that language. Now you see what happens is this, that when this positive terminal, when these positive charges flow from the positive terminal through the load, and they come at the other end, which is the negative terminal. Now at that stage, these charges have to be pushed up the potential hill. See, because they have come down the potential, and let's not worry about at this moment what the load does, but it has come there. Now if you want to maintain a current, then what you have to do is to, inside the battery, you have to push them up. Now a mechanical analogy will help. So suppose I have this following situation. Supposing I have some marbles which are at a certain height, it's moving there, and let's suppose there is a small orifice through which the marbles drop down. So since the marbles are continuously coming in, as long as you are pushing from here, the marbles will come through this. But once it has come to the ground, there is no way it is going to return back. So what we do is this, that we have a person who is standing at the ground, who actually picks up these marbles and put them up there. And that is the only way you can continue a regular circulation of marbles in this mechanical analog that we have given. So battery does exactly the same thing. So what it does is, these positive charges which flow there and arrive there, so it needs to provide additional potential energy to it, so increase its potential from here to there, and that's the job of a pump. So this is the job of a battery, and this quantity, the battery is there, which, because of this analogy that I have given, it looks like there is some force which is pushing it up, and because of this unfortunate analogy, this came to be known as a seat of what is known as the electromotive force. In short, EMF. In tune with our analogy, this source of EMF will do work because it is lifting it up or increasing its potential energy by moving the charges from a lower potential to the upper potential, to a higher potential. So the source, this moves charges, in this case positive charges, from lower potential to higher potential. And so therefore this source, it has to do work, and if you define the EMF as the amount of work you need to do to lift a unit charge, then I define my EMF as work done per unit charge. Now notice, this doesn't even have the dimension of a force, but nevertheless this is called electromotive force. So this is equal to, suppose work is represented by W, so this is dW by dQ, and whose units, as you can see, this is work, so therefore it is joule per coulomb, which is called a volt. So this EMF is not a force. But EMF provides a mechanism to continuously lift the potential energy of the positive charge so that it can start continuously flowing. So therefore, let us quickly summarize what we have learned regarding our flow of current through a resistor. So consider a typical resistor of length L. So supposing the electric field direction is this, by that I mean this is at a higher potential, and this is at a lower potential. Of course, the current density direction is also this. The various relationships that I have got are the following. I have E equal to V divided by L, which is simply the electric field being potential difference per unit length. the current density is related to the electric field by J being equal to sigma times E. Alternatively, my E is equal to rho times J. Now I know that the current I is related to the current density by J times the area. So if you look at these relationships, we get the following. We get E equal to V by L, but E is also equal to rho J. These are magnitudes I am writing down. And so this is equal to rho J. J is current I divided by A. So therefore, my potential difference is related to the current by this relationship, that it is given by rho L over A. Let's put this dimensional quantities and quantities specific to the sample dimensions times I. Now this is the quantity which we call as the resistance and is usually denoted by R. So I find that R is equal to rho L over A, that is the resistance of a sample is proportional to the length of the sample and is inversely proportional to the cross section. Now, an ideal source of EMF provides a constant potential difference or constant voltage across its terminals. Now, this is irrespective of how much of current flows there. So, let me look at this section of a circuit. Supposing I have a source of EMF and let's say there is an internal resistance and this is my battery. So let me represent it the way I have been doing. So this is EMF E, this is the internal resistance R, this is the point A and this is point B. For definitiveness, let me take that this EMF is 10 volts. So this is the positive end of the battery, this is the negative end, and suppose I am interested in finding out what is the potential difference between the points A and B. So what is delta V AB? Let me define an intermediate point which is C. It really doesn't matter whether you put the internal resistance to the left of the battery or the right of the battery. For the purpose of illustration, the result turns out to be still the same. Now, clearly, the potential difference across AB is the sum of the potential difference across AC and CB. So, let me write this, that delta V AB is delta V AC plus delta V CB. Now, had there been a current in the circuit, and suppose that this is the current which is flowing from the positive terminal out, then this term would have been I times R plus of course delta VACB, delta VCB. But because there is no current, so this term is 0. So I am left with simply delta VCB, but that is nothing but 10 volts. Now, whatever I have said is true, provided there is no current in the circuit. In other words, if it is an open circuit, if the circuit is open, so the open circuit voltage is 10 volts. Of course, if there were current in the circuit, the voltage that will be available across the point A and B will be smaller by the amount I times the internal resistance R. Let me take a specific example. I take the same battery, but let us say that this is my source. There is an internal resistance here. So let me just mark it with a block to show this is my battery. And there is a load, that is the outside resistance through which I am connecting this. So let's just call this RL. This is the load. Let me give some numbers. Supposing the internal resistance is 1 ohm, and let's say the battery provides 10 volts open circuit voltage, then and let me say that this load is 4 ohms. Look at what happens there. So the net potential difference now is, I can go from any point to come through it. So therefore V will be equal to I times R total. Now notice that since I am essentially in the same path, the current cannot change in that path. So whatever is the current, it will first go through RL, then through this. So therefore this will be equal to I times RL plus R, and that's equal to 10. So therefore my current is 10 divided by 4 plus 1 is 5, which is equal to 2 amperes. Coming back to what is the difference between, potential difference between the point A and the point B. So you notice what has happened there. So since a 2 ampere current is passing, I have an additional drop of 2 amperes multiplied by that. So so therefore this is VAB is I times RL, if you like. You can do that, and that's equal to 8 because I is 2 amperes, RL is 4. Now another way of looking at it is, you go to this intermediate point C that I talked about. So then we say that, look, VAB is VCB minus VAC, and that's equal to 10 minus 2 into 1, because 1 ohm is the internal resistance, which is also 8 as it ought to be. So let me continue with this and try to tell you how does one find the potential drop. And this is very important because lots of students have confusion on how to go about it. Let me do that by an example. So once again I take a battery, internal resistance. So let's suppose the internal resistance 3 ohms, and my battery as before is supplying 10 volts. And let us suppose that I have a current, this I have actually measured, and there is a load there through which the current that passes, okay, is let's say 0.5 ampere. So look at what happens there. The potential difference that exists between the two ends of RL is also the potential difference that exists between these two, because these wires are supposed to be resistorless. So therefore, if the current passing through is 0.5, I times R is the potential drop here, which is 3 into 0.5, which is 1.5. So that potential drop between these 2 points is 8.5 volts. But you see, it is the same current which is passing through RL. So therefore, 8.5 volts divided by RL is equal to 0.5, which tells me that the load must have been 17 ohms. How does one do it systematically? So the way to do it systematically is the following. So let's repeat that problem in a slightly different manner. So supposing I have a circuit of this type. I have two resistances, R1 and R2, and these are in series and connected with a battery. Battery may have an internal resistance, but we are not particularly worried about that. And so this is my battery, which provides an EMF E. So let's look at what happens when I look at various points like A, B, C, D and try to find out what is the potential of a particular point related to the other point. Let us suppose we are going against the direction of the current. Now, in this particular case, because there is a single battery and this is the positive terminal, the current is obviously moving like this. So let me start at the point C and start moving in the direction opposite to the current. So notice this, that as I cross R2, reach the point B, my potential will rise by an amount I times R. So let me write this way, that Vc plus I times R2 is equal to Vb. Continuing like this, let me go to the point A. So my Vb plus I times R1, that is the rise in the potential as you move from B to A, and that's equal to Va. So therefore what I get is Vc plus I times R2 equal to Vb, but Vb is Va minus I times R1. So that tells me that Vc minus Va, or rather I should say Va minus Vc, is I times R1 plus R2. So therefore, the current I is given by Va minus Vc divided by R1 plus R2. But you observe that Va minus Vc, since these are connected to the battery by the resistanceless wire, so this is equal to whatever EMF is supplied by the battery. This is not exactly the open circuit EMF because there is a current in the circuit. So there would be a drop through the internal resistance, but this is given by the EMF available to the circuit divided by R1 plus R2. And as I have pointed out, if instead of going in a direction opposite to the current, if you traveled in the direction of current, all that you have to do is to do a similar exercise by saying every time you cross a resistance, the potential drops. So what is the effect of the internal resistance? So the internal resistance of the battery reduces the voltage that a battery may be able to supply by an amount I times the value of the internal resistance. And obviously, this means that if a battery is in a circuit which has a current flowing through it, the effective voltage that it provides becomes reduced. So let me give an example where we calculate this on a slightly different problem. So let me take an example where I have two batteries. So this is one battery. This is the internal resistance is R1. There is another battery, but this time I have written it in a slightly different way. That is, the polarities are different. And so this is second battery. So let's call this R2. And normally a C-top EMF is shown in pictures in this fashion, going from negative towards positive, because you are increasing the potential energy. So therefore, let's call this E1, which is equal to 2 volts battery, and E2 is equal to 4 volts. And I have given some data. Let me take R1 to be 1 ohm and R2 to be 1.5 ohm. And this whole thing passes through a load resistance RL, and let's take this to be equal to 5.5 ohms. Well, let's look at this problem. This is a problem where I am interested in finding out how much is the current. Now, there is no particular place where I can start with. So let me start here. Now, having done that, I would go look at this situation here. This is purely intuitive. I have a 4 volt battery here and a 2 volt battery here. This terminal is positive, so I expect the current to go in this direction. Let me not put the direction directly, but I say that let this be the assumed direction of the current. And this is purely because the positive terminal of a higher potential, higher voltage battery is going to provide me current in this direction. I need not really have assumed it, but we will show that in a problem. So let me do the following. Let me start from the point A and proceed in a direction opposite to, okay, in the direction of the direction opposite to the current. So what I do is this. We say VA now minus, because my potential is dropping here. There's a positive to negative, minus E2. Let's assume the current to be equal to I. So plus IR2, about whenever you assume that there is a current flowing through a potential resistance, the potential drops. So plus IR2 plus IRL plus E1, well, plus IR1 plus E1. Now see, I am back at A, so therefore this must be VA. I have simply completed the same circuit. From here to there, here, there, from this path there is no potential drop, here and this. So I have traveled like this, and so this tells me that I times R1 plus R2 plus RL plus E1 minus E2 is equal to 0. Let's put in the numbers. So I've got I, R1 is 1, R2 is 1.5, this is 5.5, so I add this up, so I get I times 8. E1 minus E2 is minus 2, I can take it to the other side and write this is equal to 2. So that tells me I is equal to 1 by 4 ampere. Now, this is what I would do if I knew the direction of the current. Now, supposing I don't. I a priori have assumed this to be, say I done this way, but let me do the other way. Now then what happens is the following, that I proceed through essentially the same set of equations, and then let's look at what happens. So we go to VA, let me go back here, VA. Now here minus E1, see I am again like in the other case, I am going from the positive terminal to the negative terminal, so minus E1, drop plus IR1, drop IRL, and exactly the same way you will come back to the point A. What will happen? Now everything here has the E1 and E2 sign has changed, so I will get I equal to minus 1 by 4 ampere, saying that my original assumption that the current was in a given direction was wrong, and the current should be in this direction. And this is the way you can always find out the potential difference between any 2 points. So for example, supposing I ask you the question, what is the potential difference between these 2 points, A and B? Well, it's the same thing again. Since you have now calculated the current to be equal to 1/4 of an ampere, assuming the direction of the current to be that, so what we do is we say VB is equal to VA minus E2 plus IR2, but that's the only resistance through it is passing. Substitute the numbers, you find VB minus VA is equal to minus 3.625. I will return back to this problem in the next lecture, but we will calculate again, show that how I calculate the potential difference between these points, assuming the current to be in an arbitrary